This video covers ridge regression and the elastic net. By the end of this video, you should understand what ridge regression and the elastic net are as modeling tools, what assumptions these tools make about functional form, feature selection, and the loss function, how each implements regularization, and compared to Lasso, what are some common properties of these models and their predictions. Thus far, we've covered one regularized model, Lasso. Remember, Lasso assumes a linear relationship between the features and labels, just like OLS, but includes a penalty in the loss function, which is the regularization parameter lambda times the sum of the absolute value of every parameter in the model. This has some desirable properties for regularization. The penalty is 0 for the simplest of all models, the one with no features, or every feature is multiplied by 0. The penalty gets larger as you add more features to the model, as you allow more of those b's to become non-zero. The penalty also gets larger for larger parameters, or parameters that are farther away from 0 in either direction. This isn't the only penalty that you could think of with these properties. So as an alternative to taking the absolute value of every parameter, you could just square them, sum them, and take the square root at the end. If you were using this as a loss function, you could still include the MSE as well. This is exactly the loss function used in ridge regression. Just like Lasso, the ridge regression's penalty is 0 for the simplest of all models, the one with no features. That penalty gets larger as you add more features to a model, and it gets larger as the parameters move farther away from 0 in either direction. So how does ridge regression compare to Lasso? The penalty still causes ridge regression to shrink the model parameters. They're generally going to be closer to 0 than the corresponding OLS models. However, unlike Lasso, here you're squaring the model parameters in the penalty. That means the set of parameters that lead to a certain value of the penalty function becomes a circle instead of a square like it was in Lasso. This circle doesn't have any corners. Remember, Lasso would generally shrink some parameters to exactly 0. These are the corners in that square-shaped penalty function. The ridge regression's penalty function is circle-shaped, and it doesn't have that property. It's going to shrink parameters, but even irrelevant features are probably going to have non-zero values for those parameters. So what does this look like? If you remember, this is the shape of the penalty function in Lasso. The dotted lines represent all of the possible values of B1 and B2 in this grid, where the value of the penalty function would be exactly equal to 1. And you can see there are corners in this function at the values where B1 or B2 are equal to 0. In contrast, this is the penalty function from ridge regression. The dotted line again shows the set of all points where B1 squared plus B2 squared, and then taking the square root is equal to 1, and that forms a circle. So suppose that blue dot is the value of B1 and B2 that would minimize the mean square error of this linear function. Just like in the Lasso case, we can imagine we can move that blue dot just a little bit towards the circle. That would increase the MSE a small amount, but would also reduce the value of the penalty function. This orange circle highlights all of the points where we could move that blue dot to, where we'd see the same increase in mean square error. We could think about allowing mean square error to increase a little bit more, or maybe even a little bit more, and so on. Just like with Lasso, there's a way that we can change B1 and B2 that increase mean square error a bit, but reduce the value of the penalty function more. But unlike Lasso, that's unlikely to be at one of those points where B1 or B2 equals 0, because the penalty set here is a circle and doesn't have any corners. So in the end, ridge regression penalizes non-zero values of the b's. Because they're squared, large values of the b's contribute much more to this penalty than small values of the b's. Compared to OLS, ridge regression is going to shrink model parameters. Many of them are going to be closer to 0. But because the penalty function doesn't have any corners, exact values of 0 are unlikely. Just like with Lasso, features that do little to explain the outcome are going to have their parameters shrunk more, but many may still have small contributions to the predicted labels in ridge regression because their parameters won't go all the way to 0. So what does this mean for ridge regression as a modeling tool? Lasso is very useful for feature selection. It would shrink model parameters all the way to 0 if the corresponding feature was irrelevant. Ridge regression doesn't do this, but ridge regression is very useful if you have features that are collinear or strongly correlated with each other. Lasso is a lot less useful in this case. In fact, both OLS and Lasso can have predictions that are very imprecise if you have strongly correlated features in your model. In contrast, ridge regression will have predictions that are much less variable, even when many of your features are strongly correlated. Just like with Lasso, in ridge regression, the scale of your features matters. Most ridge regression packages are going to rescale features in the background, just like they do with Lasso. But this means, again, that there's no one definitive ridge regression model because there is a rescaling that happens in the background. Also, just like with lasso, training a ridge regression model requires a choice of lambda, the regularization parameter. This is usually determined by cross-validation, but there may be other approaches to determining it as well. So in summary, comparing lasso to ridge regression, both of these modeling tools are going to shrink the model parameters compared to OLS. The important thing to remember is that lasso's penalty function has corners at the zeros, so irrelevant or weakly relevant feature parameters are going to be shrunk to exactly 0. Ridge regression's penalty function doesn't have any corners. Irrelevant or weakly relevant feature parameters are still going to be smaller than OLS, but they probably won't go all the way to 0. This allows for many features to have a small influence on predictions. Also, ridge regression is going to place a much larger penalty on large parameters in your model. This gives ridge regression its advantage. It tends to produce predictions that are much less variable when you have strongly correlated features in your model. So lasso models are going to tend to have many 0 parameters. This easily translates into feature selection. You can just assume that features with a 0 parameter are likely not relevant. It has less to say about how relevant the features it decides to include are. Ridge regression will have few, if any, 0 parameters. This allows for many features to have an impact on your predictions, and it tends to produce models that have less variability when your features are strongly correlated with each other. So is there any way that we could combine the advantages of these two approaches? There's one straightforward way to combine them, which leads us to the elastic net. The elastic net is a modeling tool that combines the penalty functions from lasso and ridge regression. Just like the previous modeling tools that we've covered, it combines mean square error with a penalty that is a combination of the penalties from lasso and ridge. You can see that here. The penalty function is the regularization parameter lambda times this sum. The first term is alpha times the lasso penalty function, and then we add that to 1 minus alpha times the ridge regression penalty function. You can see that there's a new hyperparameter in this loss function. This hyperparameter alpha is called the mixing parameter. It's a number between 0 and 1. The elastic net penalty is just a weighted average of the lasso and the ridge regression penalties, where the hyperparameter alpha determines the weight you place on each of them. Suppose alpha is equal to 1. Then we're going to place a 1 in front of the lasso penalty and a 1 minus 1 in front of the ridge regression penalty. That will simplify, and you wind up with just the lasso penalty. So setting alpha equal to 1 in the elastic net is just the same as running lasso. In contrast, if you set alpha equals to 0, you'll place a 0 in front of the lasso penalty, a 1 minus 0 in front of the ridge regression penalty, and that simplifies just the ridge regression penalty. So when alpha is equal to 0, the elastic net is just ridge regression. Any other number you choose between 0 and 1 would just create a weighted average of these two penalties. That's why we call alpha the mixing parameter, because it defines the mix of the lasso and the ridge regression penalty that we're going to use in our modeling tool. So compared to lasso and ridge regression, what does the elastic net penalty function look like? Well, it depends on your choice of alpha. So here, I'm showing the shape of the penalty function when alpha equals 1. Remember, this is the lasso case. The penalty function is shaped like a square with corners at zeros. As I decrease alpha to 0.9, 0.8, 0.7, you can see that the corners of the box are becoming less pronounced and the sides are becoming more rounded. This proceeds all the way until alpha is 0 and the shape of the penalty function is a circle. So what does this imply for the properties of the elastic net? It's going to penalize non-zero values of the b's, just like the lasso and ridge regression. Large values of b are going to contribute much more to that penalty than small values. Compared to OLS, the elastic net will shrink model parameters. Many of them are going to be closer to 0. The penalty function corners get sharper as alpha gets closer to 1. And what that means is if alpha is close to 0, you can expect very few 0 parameters. As alpha gets closer to 1, you can expect more and more exact zeros in your parameters. Just like with lasso and ridge regression, features that do little to explain the outcome will have their parameters shrunk more. But as long as alpha is less than 1, many are still going to have small contributions to the predicted labels. It's important to note that training elastic net models requires that you make decisions now about two hyperparameters: lambda, the scale of the regularization penalty, and alpha, the mixing parameter. So how do you determine the correct value to use? Just like in other cases, there are a bunch of different approaches. You might use your understanding of the data or the process you're trying to model. You might just make a guess. You may use a formula, or you can use cross-validation. Just like with determining the value of lambda, determining the value of alpha is often accomplished using cross-validation.